title of my talk is Proof of Concept of QKD. I'm Mikio Fujiwara from NICT, Japan. Contents of my talk are following. I'd like to introduce activities of proof of concept of QKD in Japan. I'll briefly mention current status of QKD performance and POC activities. And I also introduced activities towards satellite QKD. Finally, I'll summarize my talk. First, I'd like to mention why we need QKD. This slide shows roadmap of developing quantum computer by giant companies. According to this slide, the universal full-scale quantum computer will appear around 2030. If the full-scale quantum computer is realized, currently used public key cryptographies RSA and ECC will be decrypted immediately. It means the confidentiality of our communication is to collapse, even those symmetric key and cryptographies have security against the quantum computers. Because initial symmetric key are shared by public cryptographies. Therefore, we need secure method to share the key. We believe a QKD will be a promising candidate. Moreover, stolen files repose backdoors in Internet encryption software. Even if the cryptographic scheme is secure, software-based key generation and providing schemes have risk of eavesdrop. This slide introduces quantum cryptography, which consists of quantum key distribution and Barnum's one-time path encryption. The quantum cryptography has information theoretical security. It can be proven to be unbreakable by limited computational resources. It is a QKD part that uses quantum nature. Random number is modulated on each photons and emitted. By using non-orthogonal states, the law of physics guarantees that eavesdropping cannot be done without error, and eavesdropping can be detected. This figure shows key generation rate as a function of fiber length. In this case, decoy BB84 protocol is assumed. If we use a QKD system with 1 GHz repetition rate, secure key rate after 50 km transmission is about a few 100 kbps. We Japanese team have maintained the integrated research system of QKD from the theory to implementation. Therefore, Japanese QKD systems have high performance and high-level implementation security. To expand the service area, trusted node-based key relay is performed in QKD network. By using this technique, secure communication between two nodes in the network can be realized. Such QKD networks have been established around the world. This slide shows a quantum internet prototype of Chicago Quantum Exchange. 124-mile quantum network was established in 2022, and QKD experiments are conducted in collaboration with Toshiba Corporation. EU has also developed a large-scale QKD open testbed with 18 POCs underway. It brings together telecommunication end user, critical infrastructure providers, network operators, QKD system providers, and digital security experts to enhance the security of critical applications in fields ranging from communications to power delivery to healthcare. Japanese QKD vendor Toshiba also participates trials in 6 countries in this open testbed. Chinese groups have operated large-scale QKD networks. The total length of the QKD network is 4,600 kilometers. Moreover, Chinese groups succeed in satellite QKD, the first in the world. Satellite fiber network integration is also be realized. In this slide, I'd like to present the history of QKD network development in Japan. Our QKD network, named Tokyo QKD Network, has operated from 2010. At UQCC 2010, we demonstrated the world's first real-time one-time part video conferencing encryption. Tokyo QKD Network has been in operation since 2010 to the present. Currently, we promote various POCs such as genomic data, medical records, financial data, biometrics data, and smart industry by using this Tokyo QKD network. As we proceed with the POCs of QKD network, we aim to make this network highly functional. We named this system as a quantum secure cloud. We define the quantum secure cloud is a distributed storage system built on a QKD network. This slide shows the concept of it. The combination of QKD and one-time part encryption realizes information theoretically secure communication. On the other hand, secret sharing, for example, Shamir's protocol, allows information theoretically secure data storage. The quantum secure cloud allows us to realize secure data transmission, data storage, and secondary use of with information theoretical security. We think QKD or quantum secure cloud should be real information which must be kept secret for a very long time. Examples of information that should be kept confidential over a long time are shown in this table. For example, If the genomic data is leaked, its effects will last for several generations. These data must be protected even if the cost is expensive. This slide shows the quantum secure cloud on Tokyo QKD Network. Following the OSI reference model, these members contribute to construct the quantum secure cloud. NEC and Toshiba have developed a high-speed QKD link, and NEC and Gakushuin University have developed a CP-QKD system. University of Tokyo, Hokkaido University leads the research of security certification of QKD systems. NICT and private company Zemtech have been developing secret sharing and secure computation systems. This figure shows the POC activities in Japan. We demonstrated performance of the quantum secure cloud at the case of medical records, genomic data, laser machining data, biometrics reference data, and financial data. These POCs include demonstration that assumes the presence of a large area QKD network. This line, like this line. This slide shows demonstration of distributed storage and quick reconstruction of medical records. In this case, we use the medical data with a standard format named SSMix2. This format has a deep directory structure, as shown here. This system is also expected to be useful for emergency medical care in the event of the disasters. In particular, Kochi Prefecture in Japan needs a medical data backup system in preparation for a major Nankai Trough earthquake. During a medical emergency, patient prescription history must be recovered within 50 seconds. In this demonstration, data reconstruction of one patient prescription history was performed from the data of 10,000 patients of 90 GB. The reconstruction time was about 4 seconds through the fiber network and less than 8 seconds by using the satellite link. In both cases, the performance exceeds the requirements. In this demonstration, we collaborate with public hospitals in Tokyo, and real QKD links are used in Tokyo QKD Network. We succeeded in daily transaction data backup of 6 hospitals in the distributed storage system in Tokyo QKD Network within 15 minutes. The data volume is about 320 megabytes. And we also demonstrated cross-reference of simulated data on Kochi Health Science Center. This slide introduced the demonstration at Sendai QKD network of 10 kilometers. Information theoretical secure multi-party web meeting was demonstrated. In this network, Toshiba QKD links are used. The average key consumption rate of this meeting about 1.6 Mbps. On the other hand, the secure key rate of QKD links was 10 Mbps. This result means the QKD link has enough performance for real-time key supply for video conference. At Sendai area, high-speed secret sharing was also demonstrated. This secret sharing scheme is based on simple exclusive OR calculation. We using such a formula. Therefore, it enables high-speed processing. The throughput of secret sharing is more than 700 Mbps. We also developed a high-speed one-time path encryption system which has 1 Gbps throughput. As a result, we succeed in distributed storage of 8 GB genomic data within a half a day. In this case, the data transmission, storage, and computation during the optimization of photonic laser parameters are securely performed using quantum secure cloud technologies. Transmission rights are encrypted by one-time path or AES by using the keys from the QKD links. Keio University performs design parameter optimization using the next-generation accelerator server. Such information data are stored in secret sharing system on Tokyo QKD Network. In the field of authentication technologies, biometrics authentication is convenient, but if the reference data is stolen, it cannot be rewritten like a password, so careful consideration is required for its introduction. On the other hand, since biometric authentication is a user-friendly technology, it can be used by people who are not familiar with the digital technologies, such as elderly, and its use would be expanded. In this demonstration, reference data for biometrics authentication are stored by secret sharing, and biometric authentication have been used for server monitoring and login for the tablet. The data for authentication are encrypted by one-time path. After successful biometric authentication, the tablet user enables to reconstruct the data of medical records. This system has operated since 2090s. Availability of this system is over 98%. The financial is extremely important for application of quantum cryptography. POCs for financial data encryption are underway in many countries around the world. Our groups tested low-latency secure communication of big financial data collaborating with Nomura Holdings Inc. and Nomura Securities Corporation. We succeed in transmission of 8 times normal volume with an additional delay of 14 milliseconds. As a result, we can confirm technical validation of QKD systems. In these demonstrations, high-speed one-time path encryption systems are used. In this slide, I focus on the one-time path encryption system. The throughput of this system is about 2 Gbps. To demonstrate of this speed, we tried real-time transmission of 4K video. The experimental setup is shown here. Transmission length is 90 km. The delay time of this system is less than 200 milliseconds. On the other hand, the standard delay time for enabled remote surgery is 215 milliseconds. Therefore, our system can be applied to telesurgery. Okay. Please confirm the delay during a data transmission with the actual video. The left screen is surgery screen, and the right screen is the image after 90 km transmission using one-time encryption. We can see this system works with only a small delay. Following slide, I'd like to introduce the satellite QKD technology. Satellite QKD will have an important role to realize the global QKD network because transmission loss in the space is negligible. Therefore, we can expand the length of QKD links. The Chinese group is ahead in the field of satellite QKD research. The Mischief satellite realized the satellite ground QKD, the first in the world. However, NICT succeeds in basic quantum communication experiment by using a small satellite in 2017. In this experiment, it demonstrated non-orthogonal polarization state discrimination. This slide shows an animation of our experiment. Small optical transponder named Sauter was installed in the 50 kg class satellite named Socrates. The experiment is to identify the non-orthogonal polarization state of photons emitted from the satellite. Using the beacon beam from a ground station, non-orthogonal polarization states are emitted to the ground station like this. And quantum limited communications are successfully achieved. Now we are developing an equipment for onboard small satellite and a mobile ground station for a low orbit satellite experiment. This is a picture of the transmitter. In addition to QKD, we are developing a physical layer cryptography of wiretap channel. In this model, we assume the eavesdropper can only attack passively. If we can estimate signal-to-noise ratio of eavesdroppers, the information theoretically secure key can be generated between legitimated pairs. This assumption is reasonably accepted for line-of-sight channels such as satellite ground communication. This secret key agreement scheme enabled faster secure key generation rate than QKD. In our system, we can select a QKD mode or secret key agreement mode. Here is a draft roadmap for implementation of QKD network. The crypto business, including QKD, is classified as a so-called regulated business. Therefore, incentives by using guidelines or standards are essential for the expand QKDs. These are our plan. At first step, the QKD network is established around Tokyo. At second step, QKD network colonies are built in big cities around 2025. At third step, integration of fiber-based network and satellite networks is realized. We hope to complete the global QKD network by 2035. This figure shows the future image of a quantum secure cloud with secure computation function. Several specialized computers, including quantum computers, are established and embedded in the quantum secure cloud. It enables transmission, storage, and second use of secret data with information theoretical security. Such a concept can only be realized with a hybrid of quantum and classical technologies. I'd like to summarize my talk. We demonstrate information theoretical secure data transmission and distributed storage at several POC activities. For examples, we demonstrated the high-speed distributed storage of 8 GB genomic data within half a day, and we think we can confirm the technical validation of QKD and quantum secure cloud. As I mentioned above, developing laws or guidelines is necessary to expand the QKD market, and we also need the security certification method of QKD system. Thank you for your attention.